BA Geography, Geographic Information System, Lesson 4, Coordinate System. Objectives. The basic principle in GIS is that the map layers to be used together must align spatially. This chapter deals with coordinate system which provide the spatial reference. GIS users typically work with map features on a plane. These map features represent special features on the Earth's surface. The location of the map features are based on a plane coordinate system expressed in x and y coordinates, whereas the location of the spatial feature on the Earth's surface are based on a geographic coordinate system expressed in latitudes and longitudes and all values. A map projection uses two types of coordinate system. In this process of projection, Earth's surface is transformed to a plane and the outcome is a map projection ready to use for a projected coordinate system. Projection converts data sets from geographic coordinate to projected coordinates, and reprojection converts from one system of projected coordinates to other system. Typically, projection and reprojection are among the initial tasks performed in a GIS project. Geographic coordinate system. The location reference system for spatial features on the Earth's surface is the geographic coordinate system. It is defined by latitude and longitude. Meridian in or lines of equal longitude parallels are the lines of equal latitude. The prime meridian and the equator serve as the baselines of the geographic coordinate system. In the plane coordinates, longitude values are equivalent to x values and latitude values are equivalent to y values. Longitude values are positive in eastern hemisphere and negative in western hemisphere, and latitude values are positive if north of equator and negative if south of equator. Approximation of the Earth. The main step for map special features on the Earth's surface is that select a model that approximates the size and the shape of the Earth, that is the sphere model, but the Earth is not perfect here. The Earth is wider along the equator than between the poles. Therefore, a better approximation of the shape of the Earth is spheroid, also called ellipsoid, and ellipse rotates about its minor axis. The geoid is an even closer approximation of the Earth than spheroid. The surface of the geoid represents the surface of mean sea level, which is used for measuring the elevation or the height of the geographic location. It is a mathematical model of the Earth which serves as a reference or a base for calculating the geographic coordinate of a location. Period to attain a better model locally, many countries have developed their own datum in the past. Among the local datums are European datum, the Australian geodetic datum, Tokyo datum, and the Indian datum. A geocentric datum has the advantages of being compatible with the GPS. Map projection. Map projection transforms the Earth's surface, typically based on spheroid in GIS, to a plane. The outcome of this transformation process is a map projection, that is a systematic arrangement of parallels and meridians on a plane surface representing the geographic coordinate system. There are some distinctive advantages in using map projection. First, a map projection allows us to use two-dimensional maps, either paper or digital, instead of a globe. Second, a map projection allows us to work with plane coordinates rather than longitudes and latitude values. Computation with geographic coordinates are more complex and can yield less accurate distance measurement. But this transformation from surface to a flat surface always involves distortion, and no map projection is perfect. That's why hundreds of map projection have been developed for cartography. Types of map projection. Map projections are divided into 4 classes, that is, conformal projection preserves local angles and shapes. An equivalent projection represents area in correct relative size. Equidistance projection maintains consistency of scale along certain lines. Azimuthal projection retains certain accurate direction. Map projection can be grouped by their projection surface is into cylindrical, conic and azimuthal. Map projection parameters. The concept of case relates directly to the standard line, a common parameter in defining a map projection. A standard line refers to a line of tangency between the projection surface and the reference globe. For cylindrical and conical projection, the simple case has one standard line, whereas the secant case has standard line. The standard line is called the standard parallel if it follows a parallel, and the standard meridian if it follows a meridian. Commonly used map projections. Hundreds of map projections are in use. To stop, commonly used map projections in GIS are not necessarily the same as though we see in the classrooms or in the maps. A map projection for GIS application usually has one of the preserved properties, especially the conformal property, because it preserves local shapes and angles. A conformal projection allows adjacent maps to join correctly at the corners. This is important in developing a map series such as the United States Geological Survey quadrangle maps. Transverse Mercator. The transverse Mercator projection, also known as Gus-Kruger, is a variation of the Mercator projection, probably the best known projection for mapping the world. The definition of the projection requires the parameters like scale factor at central meridian, longitude of central meridian, latitude of origin, false easterning, false nothing. Albers equal area conic. The Albers equal area conic projection has the same parameters as the Lambert conformal conic projection. In fact, new two projections are quite similar except that one is equal area and the other is conformal. Equidistant conic. The equidistant conic projection is also called the simple conic projection. The projection preserves the distance property along all meridians and one or two standard parallels. It uses the same parameters as the Lambert conformal conic. Web Mercator. Both Google Earth and Microsoft Virtual Earth uses Web Mercator. This is the Mercator projection based on sphere instead of spheroid. This simplifies the calculation because Google Earth and Microsoft Virtual Earth are primarily used the map display rather than numeric analysis. The loss of accuracy in projection by using a sphere is not deemed to be important. With Web Mercator, GIS users must consider reprojection when they want to overlay GIS layers on Google Earth and Microsoft Virtual Earth for data analysis. Projected coordinate system. The projected coordinate system is built on a map projection. Projected coordinate system and map projection are often used interchangeably. For example, the Lambert conformal conic is a map projection, but it can also refer to a coordinate system. In practice, however, projected coordinate systems are designed for detailed calculation and positioning and are very typically used in large scale mapping, such as at the scale of 1:24,000 or large. Accuracy in the feature's location and its position relative to other features is there the key consideration in the design of its projected coordinate system. To maintain the level of accuracy designed for measurement of projected coordinate system is often divided into different zones, with each zone defined by a different projection center. Moreover, a projected coordinate system is defined not only by parameters of a map projection it is based on, but also the parameters of the geographic coordinate system, example datum, that the map projection is derived from. All mapping systems are based on spheroid rather than sphere. The difference between spheroid and sphere may not be a concern for general mapping at small map scales, but can be a matter of importance in the detailed mapping of land parcel, soil polygons or vegetation stands. 3D coordinate systems are commonly used in United States. The Universal Transverse Mercator UTM grid system, the Universal Polar Stereographic UPS grid system, the State Plane Coordinate SPC system. As a group of coordinates of these common systems are sometimes called the real world coordinates. The Universal Transverse Mercator UTM grid system. This system is used worldwide. The UTM grid system divides the Earth's surface between 84° north and 80° south into 60 zones. Each zone covers 6 degrees of longitude and is numbered sequentially with zone 1 beginning at 180° west. Each zone is further divided into the northern and southern hemispheres. The definition of a UTM zone therefore carries a number and a letter. For example, UTM zone 10 north refers to the zone between 126° west and 120° west in the northern hemisphere. Each UTM zone is mapped onto a second class transverse Mercator projection with a scale factor of 0.9996 at the central meridian and the equator as the latitude of origin. The use of the projection for the UTM zone is designed to maintain the accuracy of at least one part in 2500 meters course in the UTM grid system would be accurate within a meter of the true measure. The Universal Polar Stereographic UPS grid system. The UPS grid system covers the polar areas. The stereographic projection is centered on the pole and is used for dividing the polar areas into a series of 1 lakh meter squares, similar to UTM grid system. The State Plane Coordinate SPC system. The SPC system was developed in 1930s to permanently record original land survey monument location in United States. To maintain the required accuracy of one part in 10,000 or less, a state may have 2 or more species owned. As example, Oregon has the north and the south is a PC zone, and Idaho has west, central and east SPC zone. The zones that are elongated in the north-south direction uses the transverse Mercator, and zones that are elongated in east-west direction uses the Lambert conformal conic. Point location within each SPC zone are measured from a false or original location to the southwest of the zone. the Public Land Survey System. The Public Land Survey System is a land partitioning system. Using the intersecting township and the range lines, the system divides the land mainly in the central and western states into 6 into 6 miles squares or township. Each township is further partitioned into 36 square mile parcels of 640 acres called sections. Land parcel layers are typically based on PLSS, Bureau of Land Management Survey records. The Geographic Coordinate Database contains coordinates, another descriptive information for section corners and monuments recorded in the PSSL. The legal description of a parcel layers can then be entered using, for example, bearing and distance reading originated from the section corners. Working with coordinate system in GIS. The basic GIS staff with quadrate system involves defining a coordinate system, projected geographic coordinates to projected coordinates and reprojecting projected coordinates from one system to another system. GIS is package typically has many options of datum, spatial and coordinate system. A constant challenge for GIS users is how to work with this large number of coordinate system. Recent tense, commercial GIS companies have tried to provide assistance in the areas of projection file, predefined coordinate system, end-on-fly projection. Projection file. A projection file is a text file that stores information on the coordinate system that a data set is based on. The projection file contains information on the geographic coordinate system, the map projection parameters and the linear unit. Besides identifying a data set coordinate system, a projection file serves at least two other purposes. It can be used as an input for projecting or reprojecting the data set, and it can be exported to other data sets that are based on the same coordinate system. Predefined coordinate system. GIS package typically groups coordinate system into predefined and customed. A predefined coordinate system can be geographic or projected, which means its parameter values are known and are already quoted in GIS package. The users can therefore select a predefined coordinate system without defining its parameter. In contrast, a custom coordinate system requires its parameter values to be specified by the user. On-the-fly projection. On-the-fly projection is a utility that has been heavily advertised by GIS vendors. On-the-fly projection is designed for displaying data sets that are based on different coordinate systems. The software package uses the projection file available and automatically converts the data sets to a common coordinate system. This common coordinate system is by default the coordinate system of the first data set in display. If a data set has an unknown coordinate system, the GIS package may use an assumed coordinate system. On-the-fly projection does not actually change the coordinate system of the data set. Thus, it cannot replace the task of projecting and reprojecting data sets in a GIS project. Coordinate system helps in adding the coordinate values to a GIS sets and helps in projection of the surface data onto the map. Projection helps in transferring the data from the globe to the planar surface with minimal distortion, and according to the requirement, different types of projection can be utilized in GIS database construction. It's very important for a location in a map to have latitude and longitude, which can be added with the help of coordinate system and projection. Thus, with the latitude and longitude of a location, the region can be identified on a GIS data.